Thank you. So thanks for having me so I can talk about our work at Priv360. This is another one of these examples where you have a really hardworking student that unfortunately isn't rewarded with a visa when they want to come and present their work. So shout out for Sheyda, who did most of this work. Now, what is the problem that we're considering? Well, just to imagine ourselves having this conference remotely, and we're doing it over VR. Now, if we're going to do that, and we want to stream it, we want to take into consideration which direction you're viewing. So if I'm looking in this direction, I want to have good quality in this direction, maybe lower quality in some other direction, so that we don't waste bandwidth. As I move my head, the server should be able to render good quality in this direction and worse in some other ones. So the server need to know our viewing direction on our pose. Now, the problem with this is that that leaves a fingerprint. So our head movements become fingerprintable. So what we're interested in this work is, can we sort of avoid this re-identification? So imagine that you have used, so we consider the problem of just taking these traces and trying to make them anonymous, but still getting a good quality of experience. So yes, one easy way is just to add a whole bunch of noise so that I do random scrambling. But the bad thing with this is that probably the quality that I'm going to get is pretty bad, because if I'm pretending to look in that direction and then I'm getting this direction, then I'm going to get bad quality. And if I switch too fast, I'm going to get sort of a lot of quality switches around me. So that wouldn't be good. So what we're interested in is really, can we get good QE and still get good prediction? Or, yeah, good head movement. So we introduced Priv360. So with Priv360, we do 4 main contributions. So we present a defense to essentially protect the identity. And the second one we're doing is that we're trying to do it to essentially provide good QE privacy trade-off. And the way we do that is that we combine sort of the noise with some viewpoint prediction and client-side adjustments. All of these things are done on client side, and we don't really make any changes on the server side. Now, we try to make this framework fairly flexible so that we can have different motion prediction methods, different type of deployments, etc. And I'll talk about some of those later. And in the paper, we try to provide, sort of evaluate the system, provide various systems insights, show results with both sort of older data sets, public data sets from 2017, as well as newly collected data sets from this year. We use multiple attacker methods and multiple objective QE metrics, as well as more sort of subjective measurements that we did through a user study. So in short, Priv360 is essentially a client-side privacy framework for 360 VR streaming that protects the users by obfuscating, but in such a way that we preserve the viewing quality. Now, the nice thing with this is that we do it in such a way that we don't require any server-side modifications. Okay, so how do we do this? Okay, so we have a client, so that's the headset, that's gonna communicate with the server. So from the client to the server, over the network, we send essentially our pose. So real time. Then the server is streaming this over to the client and sort of rendering it. That's the basic model. And our defense is gonna be on the client side. So I'm gonna focus in on the client side. This is essentially where we're doing our heavy lifting. So the first thing we're gonna do is that we're gonna take the pose. So it's gonna be some signal in 6 degrees of freedom. And we're gonna add some noise. So Gaussian noise was the simplest we started with. And then we're gonna do some head movement predictions. We're gonna use different filters to sort of smooth things out. And then we're gonna send this over the network. The server is gonna do it rendering based on sort of the claimed head movements. And then based on that, we're going to adjust for the actual head direction that we're having. And hopefully going to get a good quality experience. So again, this is maybe the direction we're actually looking. This is the one that the server get. So the server is going to optimize based on this. So we're going to see that in the direction that we're claiming to look, we might get ultra high in that direction, but lower in some other directions. Whereas when we then look at what we're actually looking, we're not going to get the best possible quality, but hopefully we're going to get good enough. Okay, that's the idea. Again, we evaluated this on 2 different headsets, one from 2017 with 48 users, and one that we collected ourselves with 28 users. Now, for all evaluations, we leave one video or one video out. We also consider sort of different number of training videos, but we never train on the video that we're actually using for the evaluation. And we use the attacker train on our on the actual perturbed data. We also consider when you don't, but for most of it, we just do that. So if we consider 3 different example attacker models, we get above 70% on the old one, and above 85 on the newer data. And we're able to get down the re-identification accuracy, in this case, to 2.08 on the old data set, which actually turned out to be what you get with random guessing. For the newer data set, we do a little bit worse than random guessing. Not sure why, but we're not doing quite as well. Okay. So that tells us that, okay, we help re-identification, but how much do we sacrifice in quality of experience? Well, to do that, we can look at, okay, what is the quality that we're seeing in this box that is our viewport? And we get pretty close quality compared to if we wouldn't have done these head movement perturbations. And we also don't see much quality switching. So it's not like we're at the other side just get a lot of quality flickering, which also would be extremely frustrating. So it seems like we have some other objective QE metrics in the paper that they all point to we're doing pretty good. But we wanted to see, do we actually do good if we implement this and test it on real users? So we have a small user study where we have three implementation. One is, okay, you don't perturb anything, you just add the noise, and then with the one that is listed as predicted here, that's our Priv360. And we can see, for example, with video quality, when they score on a scale 1 to 5, we essentially get the same video quality. And one thing is that there's no dizziness. So you could imagine that, okay, if I add a little bit of noise, it might feel bad as a user. Turns out that we're able to protect against that. So both are objective that we saw before, and these subjective measures seem to point to we're doing a pretty good job while protecting against re-identification. So to summarize, we presented Priv360. So it's a client-side defense for privacy-aware 360, where we use a combination of perturbations, viewport prediction without requiring any server-side changes. Through this, we reduce the re-identification to near random levels, and we preserve the user experience so that as well as comfort. This works across different predictors, attackers, data sets, system settings. So we have a rich set of experiments in the paper, validated both on the old data set as well as the newly collected data set, and a small scale user study. If you want to read the paper, you can find it here or come and talk to me in the break. Yeah, see you there.